Great. Thank you very much. It's my pleasure to be here. Thank you, Anne, for the introduction. Thank you to all the organizers for inviting me to participate in this symposium. I'm really enjoying all the talks, all the great science, all the discussion, and hope to contribute more towards in that direction. I'll be bringing up some points that have been brought up already and adding to that. Looking forward to many more discussions the rest of the day and tomorrow. So yeah, what I'll be talking about is designing new catalysts and processes for the sustainable production of fuels and chemicals, really with an angle of how do we use renewable resources to power these things. And before we move any further into that topic, I want to take a moment and let's all acknowledge one of the greatest achievements in the history of humankind, and that's the development of the modern fuels and chemicals industry that we have today. It is absolutely extraordinary that Mother Nature took millions of years to produce these materials, these carbon-based molecules underground, and human beings for decades and for centuries have developed the science and technology to figure out how to extract that resource and process it and distribute it around the globe at enormous scales. These are molecules that allow us to live the way that we do. And we're looking at just a few examples on the screen here. We've got hydrogen. For those who thought that hydrogen is a thing of the future, how about today, 65 billion kilograms a year production rate of hydrogen. Divided by the 7 or so billion people on Earth, that's 9 kilos per person on average per year. Absolutely massive. Comes from fossils, mostly from steam methane reforming. Where does that hydrogen go? It goes a lot into ammonia. Ammonia is another big ticket molecule, 180 billion kilograms a year. Half the fixed nitrogen in your body right now from the breakfast that you ate this morning and the dinners the night before touched one of these iron nanoparticles and came out in one of these trucks and got distributed into the food that we eat today. We make plastics. I worked at this particular facility. It's now a Dow facility, formerly run by Roman Haas. Worked there as a bachelor's chemical engineer straight out of college. Making, in that case, it was monomers, it was acrylic acid and acrylates by the megaton. If the whole plastics industry is about 300 billion kilograms a year. And then this is an oil refinery in Baton Rouge run by ExxonMobil, just one of the many oil refineries, 700 oil refineries globally that contribute towards producing gasoline at a rate of about 1 trillion kilograms a year. It's absolutely stupendous that we've been able to create this infrastructure, but it's not perfect, and we know that. It's not sustainable. That's number one. Number two, while it reaches billions and billions of people globally, it doesn't reach all billions of people. So there's an energy access question as well. Many other issues. The point is, can we come up with something better? And so this is a very tough challenge because that industry is doing extremely well thanks to the ingenuity of humans over many years. But we do have some game-changing forces in play. This is one of them. The dropping price of renewable electricity. We're just looking the last decade, since 2009. These are levelized costs of electricity in dollars per megawatt hour that has dropped massively, both for wind and for solar. These numbers where we're at today, unsubsidized, about 4 cents a kilowatt hour. And those of you who pay your electricity bill at home, 4 cents a kilowatt hour probably sounds pretty good to you. And those prices continually drop in many places. It's already at price parity or better than what you can get from conventional, say, gas turbines. So this is a really interesting opportunity. How can we use electricity to make the same types of fuels and chemicals that we use today? And it's important to also recognize that electrochemical manufacturing is not a new thing. It's been done for many years. Every time you pick up a can of soda, you're touching a piece of aluminum that was once underground in the form of ore. It was mentioned earlier. A lot of electricity globally, about 27 gigawatts of electricity goes into making the roughly 15 billion kilograms a year of refined aluminum. By the way, another reminder, please recycle your aluminum cans. It takes only 5% of the energy to get it back, as opposed to doing this all over again. Chloralkali, very important, sodium hydroxide, chlorine. These are other big-ticket molecules, around 50, 60 billion kilograms a year, consuming about 11 gigawatts, another large-scale electrified process. And hydrogen. Back in the day was actually, this was a conventional way to make hydrogen, or one of the conventional ways. You're looking at a Norsk Hydro plant in the 1950s in Norway, where they've got, of course, a lot of hydropower, very inexpensive electricity, and so they would rack up this bank of electrolyzers to make the hydrogen, which fed ultimately Haber-Bosch facilities to make the ammonia that I talked about before. Now that came out of fashion as the prices of petroleum feedstocks were plummeting, but now it's coming right back into fashion. So just some examples that this has already been large-scale deployed types of technology. How can we build on it to make it better? How do we create a new paradigm, in other words? So very simple equation here. Production costs, dollars per kilogram, is a function of your CapEx and your OpEx, and we need to hit some pretty aggressive targets if we're going to flip this industry and do things differently. Number one, renewable electricity. I'm really fired up about 4 cents a kilowatt hour. We need to be down closer to about 1 cent a kilowatt hour, I think, to really be the big lever to make this work. Another thing is energy storage. We had a great session this morning on energy storage. Of course, the renewable electricity is phenomenal. That price will continue to drop, but as it penetrates the market, what are we going to do with stranded electricity? Do we want to run chemical processes on a duty cycle that looks like that coming out of a wind turbine or a PV? Maybe we do, maybe we don't. Having some really inexpensive energy storage would certainly help us keep to closer to 100% duty cycles. If you want to make a carbon-based product, you need to get that carbon from somewhere, and nominally not from a fossil fuel if you want to avoid fossil fuels. And so if you want to grab it from air, let's say from that CO2 in the air, $30 a ton. You need a really inexpensive feedstock. And the last and the fourth very aggressive number I'm putting out here is the box, the electrolyzer. You feed in carbon, you feed in the renewable electricity. Perhaps it was load balanced with some energy storage. You need the box that takes all these inputs to make your output to do the chemical conversion to about 20 cents a kilogram. So where do these numbers come from? It's really simple. If you look at any large ticket commodity chemical or fuel, it's about 50 cents to $1 per kilogram. Think about that for a moment. What can you buy on any store shelf for 50 cents to $1 per kilogram? Not a whole lot. That's what that's what plastics, that's what fuels, methanol, et cetera. That's what basically their price is, ammonia as well. If you add up these numbers appropriately, you can hit that 50 cents to $1 target. But these are really aggressive. And so it's not impossible. It just means we have a long way to go. We've got to keep pushing forward. I'm going to be focusing on what's inside this box, this kind of CapEx. How can we come up with better catalysts for better processes that can get us to reduced CapEx? And the goal here is, of course, to make all the fuels and chemicals that we need today and will be needing in the future, but coming through these renewables. So we need fuels for transportation, we need materials, we need chemicals, we need fertilizers, et cetera. And can we take renewables, whether it's direct sunlight or electricity or what have you, and do the chemical conversions from molecules that we have in abundance, nitrogen that we're breathing, CO2 that we're breathing, water that we're breathing, methane, which is lower carbon feedstock than most fossil fuels that we use. And how can we chemically convert it, either with photons directly or with electrons, which maybe give you the product you want directly, or you can feed that into, say, the modern chemical industry as we know it, which is really based on temperature pressure processing to make the products that we need. So there's a lot of room for invention. This is not meant to encompass all possibilities. Then it would be intractable and impossible to read. It's just to really serve as inspiration, as we need to come up with some new routes based on some new feedstocks and new energy sources. So what I want to talk about in that vein are really three different chemistries that I'll be touching on, building on some of the discussion points earlier. Talk about hydrogen first from water, making carbon-based products from CO and CO2 reduction, kind of leveraging a lot of things that Mark was talking about earlier, and then we'll talk about ammonia. So let's talk about hydrogen first, and I really see this as the flagship. This is the furthest ahead of all these technologies. This is a concept plant that Proton Onsite, which is now owned by Nel, which is Norsk Hydro. This is their techno-economic analysis of what PEM electrolyzers could look like if you're going to make a large-scale facility making 50 tons a day production. It's about a 100-megawatt facility if you want to put it into those types of numbers. And chemical engineering 101, I should say, when you're doing chemical engineering plant design, you start with your reactor, which in this case is banks of electrolyzers. These are the small gray boxes that you see on the diagram. And it's not just about the heart and soul, which is the reactor. You need to get the balance of plant. You need water management, you need hydrogen management, you need power management, et cetera. You add all that up, and you end up with this pie chart of where the costs are coming from. And you can see that there are a lot of levers here, and there's not a single lever alone that is going to get us to where we need to be. But the biggest chunk of the pie is in the stack itself, the 54% you see, and a big chunk of that is the precious metals. They use platinum and iridium catalysts. Now, they're projecting 50 to 60 cents per kilogram of hydrogen. This is like their forward-looking models with additive manufacturing and reducing precious metal content and all these good advances. That's still much further north than the 20 cents that I was mentioning on the previous slide. So I think there's a lot of opportunity. We've got to keep pushing forward. I mean, they're not even there yet. Nobody's there yet. But there's a lot of R&D that needs to get done. So in our group, we've been working a lot on non-precious metal catalyst development. It really started from theory, in fact, looking at hydrogenase and nitrogenase as enzymes. This is publications that came out in 2005, Berit Hinnemann and Jens Nersko. And that really inspired us to look into sulfides, nitrides, phosphides, carbides, us and many, many other people who are in this in our community. And the bottom line is MOS2 is just one example of it. These nano triangles, again, inspired a lot by what you see in Mother Nature, turned out to be pretty good catalysts in acid. And so this is work as a postdoc, working with Yves Korgendorf and others in Technical University of Denmark. And then my research group at Stanford developing all kinds of different formulations of sulfides. As you can see, nanowires, nanoporous materials, small molecular clusters. These are Jabo and Jakob, one of the first PhD students and postdocs to join the group. And these were very active. And we were very excited, non-precious metal catalysts. They're showing activity. One of the challenges is that in this case, we were doing things in a very fundamental way, which is great to get some information, but we're running about 10 milliamps per square centimeter. I should be clear, these are not as good as platinum. No human on Earth has ever made a non-precious metal catalyst that's as good as platinum. But we're getting somewhere. And the question is, what can we do from there? And so we translated this. This is the work of Desmond, a further PhD student along the program, who then took a lot of these formulations of sulfides and phosphides and phosphosulfides and made them into inks. And we said, well, let's make our own home-built water electrolyzer. So this is what it looks like, a very modest 5 square centimeter thing. This is Nafion, conventional plastic that used to conduct protons, carbon gas diffusion electrodes, and he basically put these inks of non-precious metal catalysts and wanted to compare them versus platinum. So he is now running these at more commercially relevant current densities of 1 amp per square centimeter. And you can see that the iridium platinum polarization curve is definitely the best of the bunch. It's the one that gives you the 1 amp at the least amount of applied voltage. But if you swap out that platinum for these different sulfides and phosphosulfides, you see that you pay only a small penalty of 0.2 volts. Now, in a perfect world, we pay 0 millivolts of a penalty, and we can get a polarization curve that looks just like the platinum using a non-precious metal. But like I said, no humans ever developed that just yet. And so there's still a challenge to be had. Nevertheless, this does present an interesting opportunity with those 0.2 volts. Now you got a trade-off that you can ask yourself, do I want to pay for a less efficient electrolyzer, but then it's lower CapEx, or would I rather have a more efficient electrolyzer and pay more in the CapEx? In a world of 10 cents a kilowatt hour electricity, it's a no-brainer. You go with more efficiency. But if it's really low-cost electricity, then maybe you're willing to pay the extra 0.2 volts. So still some development to be done, but we're entering some interesting phase space. Now, how long do these things last? We got working together with Proton Onsite that I mentioned earlier today. We were awarded an SBIR through the U.S. Navy. Naval submarines also care a lot about water electrolysis. They care actually more about the oxygen, as you can imagine. If you were a sailor 100 meters below water, that's what you'd care about more. But the point is, this is a water electrolyzer on a U.S. naval sub actually reflects a lot of what we're finding on ground, which is low-cost electricity. They've already put the sunk cost in a nuclear reactor that's portable in the sub, and dialing up the nuke to give a little more electricity costs them marginally nothing. So for them, CapEx is everything. So they wanted non-precious metal systems in electrolyzers. So we work with Proton Onsite. This is a commercial-grade system. They literally sell this with platinum and iridium. It's a 86 square centimeter membrane electrode assembly. It's 400 psi output pressure of hydrogen, 50 degrees C, and is driven at 1.8 amps per square centimeter. And so we, meaning Mackenzie and Lori, prepared catalysts of non-precious. We prepared a number of different ones. I'm showing you the example of cobalt phosphide, high surface area formulations. We ship them off as a powder to Connecticut. We're not allowed to know the secret sauce that they used in making these things. They just kind of pretty much took their normal preps as if it were platinum and integrated it into their cells. And what you see is it performed extremely well. Again, you see now it's driving 1.8 amps per square centimeter. And again, you're paying that 0.2 volts, which is exactly what we expected based on the slower turnover frequency of non-precious metal catalysts. What about the stability? They ran this as long as they were willing to, which is about 1,800 hours, and it was stable. And the turnover number here is about 10 to the 5. So it's like about 100,000 H2 molecules per cobalt phosphide unit in the system, and there was no sign of degradation at the end. They shut down the experiment because it was the last day of that SBIR. I don't know if it would have lasted another 10 minutes or another 10 years. That remains to be seen. But this is really exciting because this is really the first demonstration of these newer catalyst formulations that are now finding their way and operating well within a true commercial reactor. Now, there's a few other things that we can do with these materials, and Ismaila gave a great talk on solar photoelectrochemical processes. We've been collaborating with NREL in this domain, so this is some work from them that we weren't involved in, where they set a record at the time a few years ago on 16.2% solar to hydrogen production. So they're taking tandem 3,5s and then putting some platinum ruthenium hydrogen catalyst, and it worked. It was one of the records out there, and it was stable only for an hour, which is pretty standard in this field. It's actually really tough conditions in acid. You're dunking these semiconductors. But the good news is that it did work for that time scale. Well, these materials that I'm describing, these sulfides, actually turn out to be pretty solid materials as well that are very stable in those types of environments. So my student Ruben then started layering, taking a lot of these tandem systems that were coming from NREL that were fabbed from the team out there, and layering MOS2 and demonstrating greater than 10 hour stability, so a factor of 10 better than the platinum ruthenium, while still maintaining very high solar to hydrogen efficiency, about 10% solar to hydrogen. Now, this might not seem very exciting to you, 10 hours. I just showed you, almost 1,800 hours. But actually, I wanted to show you this plot. I know it's hard to read, but I'm going to walk you through it. This is basically unassisted water splitting, and really to show you that durability is a major gap, and that's a theme that has been brought up already. So on the bottom axis is solar to hydrogen efficiency. I asked Ruben to plot on one plot every single unassisted water splitting system with greater than 1% solar to hydrogen. And you can see all these discrete points on the plot. There's not that many. We can count them on our fingers and toes. And then that's the x-axis is solar to hydrogen efficiency. Where you want to be is the PEC goal as directed by DOE is we want to get to 25%. What about stability? These are liters of hydrogen produced, milliliters per square centimeter. And the point I want to make is this is a log axis on the Y scale. And you can see that none of these points are anywhere close to where the PEC goal is. And just for reference, if you took a typical commercial grade photovoltaic and converted into these units, it would be this dot up here. So you can see that stability is a very important metric. And the simple point I want to make here is that, yes, we've been getting better and better making it high efficiency systems, but the biggest gap is not going from, say, 19% to 25%. It's going to 2 orders of magnitude or 3 orders of magnitude or 4 orders of magnitude to get up to the stability gap. So let me switch gears for a moment and talk about carbon-based products. And there's a great team of researchers I want to thank on this who've contributed in so many ways. Some have contributed on the order of months and some an entire PhD thesis. Start with Kendra, Natasha, and David, which are our first 3 PhD students to work in the space. Kendra and Natasha have since gone on to found a company in CO2 electrolysis called Opus 12. I'll be showing a lot of work from some other researchers, Steph Nitopi, who recently graduated, Carlos Morales-Guillo, who was a postdoc, is now at UCLA on a faculty position, Lei Wang, who's a postdoc in the group, and then Chris Han. Chris Han was a postdoc in the group about 6-7 years ago and is now an associate staff scientist at SLAC, an up-and-coming scholar in the field, somebody to pay attention to. Absolutely central to everything that we do on CO2 electrolysis these days. So getting to the techno-economics, long story short, the techno-economics look good. If you can make materials and devices with the desired properties, the desired catalyst with the right selectivity, you need good mass transport, you need all kinds of assumptions in there, but nothing out of reach, nothing out of reason. And it depends on your product. Are you making carbon monoxide? Are you making ethylene? Are you making something else? Basically, one of the bigger drivers is, of course, the cost of electricity. I mentioned we need to be really down close to 1 cent a kilowatt hour, and now you can see why. You also need really good energy conversion efficiency and all these other things that we don't have today. So big R&D challenges, but the techno-economics basically say it's worth our while to do the fundamental R&D. Now, is it easy to make carbon dioxide, turn it into fuels and chemicals? It turns out to be a lot easier than we ever anticipated. There's still a massive amount of challenge, but basically you're taking a bottle of Perrier, bottle of San Pellegrino, sticking in a copper electrode that you just kind of polish up. Polycrystalline doesn't mean to be terribly fancy, and this is what it does. It'll make 16 different products for you at STP. And that's exactly what Kendra and Natasha and David had done. And in this case, what they were really doing, they weren't doing as much catalyst development as reactor engineering. They designed reactors to give us really good sensitivity to identify and quantify the products of reaction. Not only could it make all these interesting things, C1, C2, C3s, different functionalities, aldehydes, ketones, carboxylic acids, et cetera, they could quantify the reaction rate as a function of the applied potential. And that's exactly what these plots are shown, just compartmentalized to make it a little bit easier on the eye. The 2 things I'll say are that, number 1, these products require a very negative voltage to get them to go. And number 2, you're typically making a big mix of stuff, which would be a separations nightmare, and there's no sense in commercializing a catalyst that works like this. So the real challenge, we think, is in terms of selectivity. How do you make a more selective catalyst? And it's tough. This is a diagram that Stephanie had put together in a recent review, showing a lot of different mechanistic pathways. When you're going from carbon dioxide, you're putting in those first 2 protons and electrons to make either formate or CO, or going further to make all these other products. This is only showing you the first 12 electron transfers and going down to C2s. There's a whole block that's not shown on C3s. Very complicated. We know very little about this diagram. It's just really just to show different kind of schools of thought on different, where different theoreticians and experimentalists are kind of agreeing or disagreeing. But there are a few things that we do know. And one of the things that we do expect, and Mark mentioned this earlier, is that formate's a dead end. And really, CO is the key intermediate to further reduced products. Still open questions on how do we suppress hydrogen evolution, as Mark was talking about earlier. Other questions are how do you favor CC coupling over C1 products? If you don't want to make methane, you want to make CC coupled products, how do you steer things in that direction? If you want to make oxygenated compounds versus hydrocarbons are great, but they're also the lowest market value. They're so cheap we burn them. How can we make something a higher market value? How do you selectively make oxygenates over the hydrocarbons? And then how do you selectively produce a single desired oxygenate without making others? So these are some of the open questions that we're trying to tackle here. Lei and Chris, wanted to look at this chemistry. CO2 electrochemistry, I already showed you what Kendra and Natasha had done. They wanted to see what happens if you take that same copper and do CO reduction in alkaline versus CO2 reduction in pH neutral. When you do CO reduction, you don't form an equilibrium with the water, so you can choose whatever pH you want. And for the reasons that Mark brought up earlier, there's a lot of advantages to going alkaline, and this is shown here. You basically make the same usual suspects of products. You make your ethylene, your methane, your ethanol, propanol, et cetera. But you make them, a lot of these products, half a volt earlier on the RHE scale, on a reversible hydrogen electrode scale. So that's half a volt of improved energy efficiency for your device. It's half a volt better for the C2 products, but only a quarter of a volt better for the C1 product of methane. And that's an interesting point. Why is this? It turns out that we think that this is facilitated, the CC coupling step is facilitated greatly by this electric field. And Mark had also mentioned this, when you have cations that are near that interface, it can really help stabilize these intermediates. And so if you're a cation like a potassium or a lithium or a cesium hanging out the interface, you don't care what the RHE voltage scale is. You just care about the absolute magnitude of the potential. So say an SHE scale or a silver chloride. And it turns out when you plot the same data in that way, you see that a lot of overlapping of the C2s, though interestingly, C1 chemistry methane is easier to make from CO2 than it is to make from CO. And we think that's because you're in those conditions, in base and CO reduction, you're depleting the carbon intermediate by making C2 so fast you can't hydrogenate it all the way further to make the hydrocarbon of methane. And so we can take this and I can dissect this in many different ways. But one thing I wanted to point out, and when we look at CO reduction versus CO2 reduction under these two conditions of alkaline versus neutral, here's the CO reduction data, here's the CO2 reduction data. And what we're plotting here is CC coupling rates. So on what you see here is the CO makes almost an exclusively CC coupled product, C2s and C3s, only a smidge of methane here, whereas CO2 makes lots of methane while it does its CC coupling. That's one point to take home. Another point to take home is oxygenate versus hydrocarbon ratio, which is the plot on the right. When you're doing CO reduction, you see a lot better oxygenate production relative to hydrocarbons than you do in CO2 reduction. And we think this is really a simple reason. The closer you operate to the thermodynamic equilibrium potential, the less reducing power you have. And so you're going to have a better chance at making oxygenates if you're to the right of this diagram than when you're on the left. Now, how can we use all that information to design better catalysts? So here's Carlos and Natasha, who started putting gold nanoparticles down onto copper. Mark had also mentioned that gold is a very good catalyst for CO2 reduction to make CO selectively. And this was our scheme. It's really a tandem catalysis scheme at molecular length scales, with the idea of you can flow in your CO2 in neutral, have the gold make your CO and create an overpressure of CO on top of that copper, which can then do the CC coupling to take it forward, and it works. And so on the left plot here, I'm showing you how many CO2 molecules are getting reduced to these greater than 2 electron products, which are oftentimes more attractive in this scheme. If you look at pure gold, it's not very good. If you look at pure copper, it's certainly decent. That's the data I was showing you earlier. If you put this gold on top of this copper, you get a 100-fold increase in the reaction rate at these lower overpotentials. And what are you making? You're making predominantly alcohols like ethanol and propanol. And so this is a way of really combining two distinctive catalysts, again, at these molecular length scales, where if you know enough about the mechanism, you can make a better catalyst system. Another interesting output is that electrode surface area itself can impact selectivity, and that's kind of weird. If you want a higher activity and more product, higher surface area makes a lot of sense. In this case, electrode surface area can also impact selectivity for the reasons I mentioned earlier, that if you operate closer to equilibrium, you have less reducing power. And so based on the supercapacitor literature, and Veronica gave a really nice talk earlier today on that, we just found some really nice preps for some really high surface area copper. And so this is what Lei did, and we tested it out for CO reduction in base, kind of throwing everything at it. CO reduction in base with a high surface area material. We can get the chemistry to go at very low overpotentials, only minus 0.23 volts versus RHE. And interestingly, it is almost 100% selective for CC-coupled oxygenates. Because you're operating at so close to equilibrium, you're not reducing it all the way to the hydrocarbons. Of course, if you tilt the voltage more negative, you'll increase the reaction rate, but you'll start to make more reduced products. And so this is giving you a lever. This is interesting. It's showing you how voltage itself can be a lever in steering selectivity the way you might want it to go. Now, if you want to make a single oxygenated compound, we thought it might be wise to tune the binding energy of oxygen-bound intermediates. So we looked at copper-silver alloys. Here's Lei and Chris again, and basically just dipping this copper into a silver nitrate solution. You can steer the selectivity tremendously. On a flat foil, you make almost 100% selectivity towards one oxygenated CC-coupled product, which is acetaldehyde, making a decent amount of hydrogen while you're at it. If you put that same type of silver on top of the copper nanoflowers, you can get at a less negative voltage, higher current density, and you make much more selectivity towards that acetaldehyde. So it's about 75% selectivity towards CO2 reduction total, and of that 75%, 98% is acetaldehyde. So really just showing you, just knowing at least a few things about the mechanism. We don't know much, but with the little that we do know, we can start to employ that to really start to tackle some of these key questions with much more to go, which a better understanding of the mechanism will help inform. Now, in my last couple minutes here, I just want to say a couple really quick words about ammonia. And again, many teammates on this one, not just within my research group, but other research groups at Stanford, Matteo Cagnello, Stacy Bent, as well as a team at Denmark led by Ib Korkendorf and Jens Nørskov. This is through a Danish foundation, the Willem Foundation, which is very interested in sustainability. And just a reminder, again, the Haber-Bosch process, as wonderful as it is, that it literally feeds billions of people on Earth. One of the big challenges is that it requires centralized facilities. That's just the nature of the thermodynamics of this chemistry. If you're running it at high temperatures, you got to run it at high pressures. Very tough to imagine distributed manufacturing of ammonia at 100 bar or 200 bar. And when you have centralized manufacturing, what ends up happening is the way that it gets distributed is that most of that ammonia ends up going off as a waste and being a real environmental issue as opposed to going into the crops where we want it. So distributed manufacturing ammonia makes a lot of sense. Farmland is distributed. What if you had a system, an electrolyzer, that would electrolyze that N2 to make ammonia? You just basically put some solar cells on your farm, and when the sun is shining and there's water present, which is exactly when the plants want to grow, you could have this electrolyzer locally make that ammonia for you with the 78% N2 that we're breathing. That is the vision. That is extremely tough. N2 chemistry at STP is another world. It is an extremely tough reaction. Theory indicates that it should be possible. These are metal catalysts that basically say, hey, if you give me minus 2 volts, minus 3 volts, I should be able to get this chemistry to go. Yeah, but you'll be making tons of hydrogen while you're at it. So it's really a selectivity problem. How do you protonate N2 and not protonate, not get the protons to make H2? That's the real question. So we came up with a workaround to address this. It's not a catalytic process. It's a cyclic process where if you give me inexpensive renewable electricity, we can plate lithium from lithium hydroxide in a molten salt. And then that lithium metal, you just expose it to N2. It'll form a nitride very readily thermodynamically. You take that lithium nitride, you dunk it in water, it'll hydrolyze, and you end up making ammonia and lithium hydroxide, which you can cycle right back and replate. You can just keep going over and over and over. So we've demonstrated this process works where 90% of the electrons are actually going to make NH3. That's a very high selectivity. What would this look like on a farm? So this is, let's say you have a 1 hectare farm that's 10,000 square meters, 100 by 100. That amount of farmland requires about 100 kilos of ammonia per year. And if you have a 90% Faradaic efficiency process like the one I just showed you, you only need 5 square meters of solar cells. That's how many solar cells of the stuff that you would normally buy, the low-cost stuff today. That's how much you'd have to occupy of your farmland to provide the electricity to make that happen. So a lot of possibilities, still a long way to go techno-economically. For those who are interested in this field, let me just say that detecting ammonia, the analytical science of detecting ammonia in small amounts is really, really tough. And we've been actually putting a lot of our effort in developing methods and protocols that we hope are going to be helpful for the community. So I would just point your attention to things that Suzanne and Adam have been working on, and we need to make sure that we're measuring. The problem is there's so much ammonia in our system and society that we're breathing it right now, and that adventitious ammonia can maybe give you a false signal. So something to bear in mind. So I'll summarize and conclude that I think there are a number of exciting electrochemical pathways to fuels and chemicals. I just showed you 3 examples. There's many more examples out there. Hydrogen production, carbon-based chemistries, and ammonia. Again, thank the many people who are involved in this and the funding agencies, National Science Foundation, the Department of Defense, EERE, and Office of Science via JCAP and SunCat, as well as a number of private foundations as well. So I thank you all for your attention. I'd be happy to take any questions.
Tom, really nice.
For the record, he said it was really nice.
Okay, got it. Really nice. You focused on these reductions, but you didn't say anything about the oxygen side. And I know that, particularly for CO2, a substantial fraction, if not most of the energy, is going into the oxygen side. What comments do you have about that?
Absolutely. Oxygen remains one of the greatest challenges. And as Mark mentioned, that there's an over-potential there for these multi-electron processes. And in this case, even Mother Nature hasn't come up with it. So as marvelous as Photosystem 2 is, even that requires an over-potential to go. And so I think there's a lot to be understood about water oxidation, and for that matter, oxygen reduction as well, as a function not just of the material, but the electrolyte. Is it an acid? Is it base? Is it neutral? We have to think of any of these technologies. There's going to be like a native condition depending on the product you're looking to make, and we need a good, probably water oxidation catalyst to couple to that. You're right. I didn't talk about it today. We certainly work in that space. One of my former PhD students in the room, Lindsay Seitz, is an expert in water oxidation. I would certainly encourage you to chat with her, professor now at Northwestern.
Great talk, Tom. Thanks.
Thank you.
One of the things I would point out that's a little pedantic, but I think is important for this workshop is when we switched from real horsepower and wood to our fossil-based and plastics, we didn't do drop-in replacement. And so I think right now there's still this little bit of a mindset that we're going to drop into the current infrastructure, and we may find that very difficult from a cost standpoint. So as we think about things like circularity, our plastics problems, our nanoparticle problems in other areas, it might make sense for this workshop to also think about what are the not-in-kind, maybe more functional kinds of products that we want to make that might make more sense by some of these methods as well, in addition to the drop-ins of where ethylene might fit into the current system or something. So food for thought, I think,
I
for
couldn't
all.
agree more, Bill. Absolutely.
Tom, I want to go back to your first topic, the hydrogen evolution at the molysulfide. Are you finding the stability is more, it's a thermodynamic rock, or as Stan pointed out, you often want soft materials because they can, in some sense, be
More dynamic.
self-reforming, self-healing, more able to recover from catastrophic rearrangement?
Great question. With the molysulfides, typically, I would say they're more like a rock. They are just very stable under acid conditions, and base they're not, and so that's also something to bear in mind. And what was different about that, and if you go to basic conditions, alkaline conditions, there's actually a lot of catalysts that are in play because they can survive under with cathodic protection. They're under these more negative potentials. But on the acid side, there's actually not nearly as many materials. And I think with the molysulfide, people had long known that it was very stable in acid, and people actually had made hydrogen measurements, some really nice, careful measurements on single crystals. Molysulfide is a mineral. You can buy a single crystal for $10. At a square centimeter size, it's kind of like, it's almost like graphite, right? It's very stable stuff.
Scotch tape, peel your electrodes.
Scotch tape, absolutely. The interesting thing was at that time when they were doing those studies, because it was bulk molybdenum sulfide or single crystal molybdenum sulfide, it didn't have a whole lot of defects, and all the action is at the defect.
At the defects, yes.
And so that is something to bear in mind because the defects are not as stable, of course, as the basal planes. And so that's something that, our measurements, they're still, even though it's a rock and thermodynamics all show it's really good, under operating conditions, it still becomes an interesting question, especially under relevant technological, formats.
But to me, that's the opportunity. we recognized 20 years ago, even with the hydrostruthenia, you wanted things that were defective to really
right.
improve new generations, new performance curves. But you have to think about how do you stabilize that chemically, physically over time.
That's right.
And to me, I've always felt the analogy is glass science. So if you've got a glass that is not a regular material, and it has a physical or chemical instability, you just throw something else in.
Yeah.
So that's where I'd like to see theory coming in, so we're not, we're marching our way through the periodic table. We're a little
Absolutely.
smarter about it.
Yeah, we have much better descriptors for the activity of a catalyst than we have for the stability of a catalyst.
Yeah. Agreed.
Yeah, super.
Tom, I was
Hi,
really
Shelley.
happy to hear you bring up this sort of concern about ammonia detection and,
Yes.
and what is ambient and what came from electrocatalysis. The electrocatalysis community at some point agreed on a set of protocols for evaluating ORR. How far is the community from doing the same thing for ammonia?
Very far, and probably the farthest. And I would say it's the CO2 even is so CO2 is much further ahead, and even that one there's not really like I would say. Standard protocols. Now, I do like the idea of standard protocols for sure. I want to be really clear that we don't want to take away the ingenuity of our community to coming up with new ways of testing things. So that should always happen. But now I think we're getting to a state, at least in CO2, and I think we're not there yet actually for the ammonia, but I think for at least for the CO2, we're there in terms of we should at least have some standard protocol so that we can do some better apples to apples comparison amongst catalysts. I think the community is ready for that. The hydrogen oxygen community has long been ready for that, and that's much further along. On the ammonia, I think it's such tough chemistry to go. It's not clear that we're ready to make those decisions just yet, but we should be thinking about it. So thank you, Shelley. Great point.
Thank you, Tom. Just to follow on the Shelley's question in the same direction, we're very thankful not only for this presentation, but for the papers that actually designated, the emissions from steaks, depending on a Texas diet or a Danish diet, how much ammonia you can actually exhale. The lithium cycle works.
It does.
And you have demonstrated that has been proven also in the hands of others.
Yes.
And this is a reality. And after this is a question of engineering to make it better. What is your attitude with respect to the plurality of reports on ammonia synthesis directly all the way electrochemically without involving cyclic reactions?
Yeah, those the reports generally involve really small quantities of ammonia and different protocols. So while we don't have protocols for the reactors and the format of the electrode and things like that, the papers that we're publishing are more like how to use N15 labeling appropriately, how to use FTIR, how to use NMR, some standard practices. And, we've made ammonia, if we looked at the standard tests that are out there, we've made ammonia many, many times with direct electrocatalytic routes. And every single time when we kept refining our protocols, every single time turned out to be not true. The ammonia was coming from somewhere else. Maybe a student was 5 meters away and opening an ammonium salt for some experiment that had nothing to do. And that little trace amount triggered it's because the amounts are so small. They're basically either you have to have really strong analytical chemical methods. And by the way, even if you buy a tank of N2, 15 labeled N2, that came from ammonia.
Sure.
And that ammonia, 15 ammonia, basically means there's a little contamination in that. So there's all these cleansing protocols that I'm not saying we're perfect on that either, but these protocols are at least a step in the right direction.
But if we go back from the detail, which are very much appreciated, do you see any catalytic system currently promising for direct synthesis of ammonia?
Not in our hands. Okay. Sorry to say.
So this is a comment about this and also the previous two presentations, which are great, as far as electrocatalysis, but they're more sort of photoelectrocatalysis, room temperature electrocatalysis, and most industrial gas processes are high temperature, high pressure processes. And so the one area that was not included in any of these discussions was a lot of high temperature electrolysis, which actually overcomes a lot of the thermodynamic penalties of trying to do this at low temperature.
That's right.
So I'm not exactly sure what the outcome of this meeting is, but I want to make sure that those types of electrochemical processes are also included in whatever we're trying to do here.
Thank you very much for saying that. Absolutely. You can do electrochemistry at high temperatures, it turns out, and there's a lot of advantages to doing so. And I think there's a different market. It's like a different, so for instance, if you're doing CO2 electrolysis and you care about carbon monoxide as your final product, then high temperature could be great. In fact, there are commercial systems. Haldor Topsoe sells one, and it works. The challenge with high temperature is actually selectivity, right? Because there you're operating at such a high T that you're really favoring thermodynamically stable products. If you want to make ethanol, it's going to be really tough to imagine that at 800 degrees C, but you can make CO or methane. And so, really, and also one of the questions is how do you follow loads? Like how important is it that you're following a PV or a wind turbine? And that's where energy storage might be able to come into play. Obviously, high temperature processes, really you pay a big price, a big penalty to be cycling up and down. Room temperature process could be much more intrinsically coupled. So not to say that there's universality to that, but this is just to give you some different flavors. And I think the bottom line is we're making trillions of kilograms of products and 70,000 different chemical products. We're not looking for a one box, one size fits all. We need many, many technologies in play, some that involve electrochemistry and some that even don't. And so I think, and even within the electrochemistry realm, there's tons of options. So thank you for bringing that up. Time for lunch. Thank you.